All right, let's go. So this integral of x to the fifth over the square root of x cubed plus 1 dx, I feel like is maybe somewhat obviously a u substitution because there aren't really any other choices. It's not integration by parts because it's not a mixture of two types of functions. I don't have a logarithm or an e to the x or a trig function. Or inverse trig, I guess, is also an option. And it's too complicated to just simplify. So I'm pretty sure it's u substitution. And there's only really one good choice for u here. You can maybe argue two good choices. I'm going to argue one good choice and say my only good choice for u is x cubed plus 1. You might, it would probably also work if you picked u equal to the square root of x cubed plus 1, but I would always recommend picking the simpler u before trying the more difficult u. Always. So then the derivative here is 3x squared. We're going to write du equals 3x squared times dx. There's a number of ways to deal with this. I like to make my thing here look like something I have in the integral. So if it were me, I would write this as 1/3 times du equal to x squared dx, because my integral has an x squared times dx. It just doesn't look like it yet. I'm going to rewrite the top as x cubed over the square root of x cubed plus 1 times x squared times dx. So if I were doing it, I would write it as the integral of, I'm going to deal with this part in a second, but the x squared times dx would exactly become 1/3 times du. Some people don't like to do this though. A different way of getting there, which will still yield the same result, we'd say I'm going to solve dx completely here and say that my du divided by 3x squared is equal to dx. That's also fine. You do it that way, you can write this as the integral of x to the fifth over the square root of x cubed plus 1 times dx over 3x squared. If you do it that way, that x squared has to cancel out. I mean, all of the x's have to cancel out, but you want to deal with that part first. So we cancel that out. That x squared cancels with an x squared here, and you're left with an x to the third. Fine either way. So then, I made a small mistake here. I wrote dx over 3x squared. It should be du over 3x squared because it's vital that dx transforms into du. But it's not just equal to du, right? You have to make sure that you capture whatever you need to capture to get there. So then writing it this way, I have an x cubed over the square root of x cubed plus 1 and a 3. I'd have the same thing here, but I'm going to start doing the u sub here. So I'm going to replace the denominator with the square root of u. And then we might see that we have an x cubed left over. And in this case, we have to do a back substitution. So we're going to take this u equal to x cubed plus 1, and we're going to solve for x cubed. So we're going to say that u minus 1 is equal to x cubed. And that is going to be what's going to go on top here. We have the same thing over here, right? This would also end up being the integral of u minus 1 over the square root of u times du over 3. So either way is a fine way to get there. After you get to your integral being completely with u's instead of x's, then we can go ahead and simplify and anti-differentiate. So I'm going to divide each thing by the square root of u. Actually, first I'm going to pull out the 1/3 because I can and I should. U divided by the square root of u is u to the first divided by u to the 1/2, which is u to the 1/2. Sorry, I wrote that kind of high. That looks really weird. And then 1 over the square root of u is u to the negative 1/2. And again, sorry for that looking kind of weird. We anti-differentiate. We get u to the 3/2 times 2/3 minus u to the 1/2 divided by 1/2 is times 2 plus c. And then since it's an indefinite integral, we have to go back to the variable we started with and write this as 1/3 times 2/3 times x cubed plus 1 to the 3/2 minus 2 times x cubed plus 1 to the 1/2 plus c. Not the worst thing we've seen. Can you explain how you got Yes. So I took this fraction here. I'm going to write it up here. So the u minus 1 over the square root of u, I'm really thinking of as u over the square root of u. minus 1 over the square root of u, which is really u divided by u to the 1/2 minus 1 divided by u to the 1/2. And that becomes u to the first over the u to the 1/2. We subtract the powers and get u to the 1/2. And here 1 over u to the 1/2 is just u to the negative 1/2. That's how we're doing that part there. Okay. Other questions about that one before we move on to the next question that was posted? So I multiplied 1/3, I think, right?
Yeah.
Sorry, so I had du equal to 3x squared dx, and I multiplied both sides by 1/3 to get a 1/3 du equal to 1/3 times 3x squared, and the 3's cancel on the right side. And so then this, I was looking for in my integral, so I rewrote my x to the 5th as x cubed times x squared. And then the x squared dx, that gets to be replaced by 1/3 du. Or you can do it this other way where you say dx is equal to du over 3x squared, and then write that in for dx, and then make sure the x squared cancels with the x squared there. Cool. Okay, moving on to Parlac number 3. Again, if you have requests, you're welcome to ask them. You can write them in the chat if you're on Zoom. Otherwise, I'll just pick and choose. So Parlac number 3. So here's what we're given for part. I should just not. I guess I'm gonna write it down. So we're told to suppose that the integral from -2 to 2 of f of x is equal to 10. We're also told that f of x is equal to f of negative x, which we should recognize as just the fact that f is an even function, right? That's what that means. F is even at least on the interval from -2 to 2. So on the interval from -2 to 2. And then they're asking us to find the integral from 0 to 2 of 5 times f of x minus 3. So I'm going to break this up. I'm going to break it up as 5 times the integral from 0 to 2 of f of x minus the integral from 0 to 2 of 3.
I thought that meant f is odd.
No, f being odd is f of negative x equal to negative f of x. Also, if f were odd, the integral from -2 to 2 of f of x should be 0, and it's not by assumption. But yeah, so this means it's even, right? This is kind of like saying, for example, if your function was f of x equal to x squared plus 2, then f of 3 should equal f of -3. And it does. F of 3 is 9 plus 2. F of -3 is also 9 plus 2. So this really does mean whether you plug in the corresponding positive number or the corresponding negative number, the y output gives the same value, whether you're to the left of the x-axis, sorry, to the left of the y-axis or to the right of the y-axis. So then we're going to use the fact that f is even to say that, oh, this integral here from 0 to 2 of f of x, this is not a bad, this is a question that is making me think a little bit. You're going to write that as 1/2 times the integral from -2 to 2 of f of x dx. Because if the function's even, then the integral from -2 to 2, right? What I'm really abusing here is the fact that the integral from -2 to 2 of f of x dx should equal 2 times the integral from 0 to 2 of f of x dx. Right? That is the quality of being even. And so I'm just dividing both sides by 2, bless you, to get that. And the reason I'm writing it that way is because I know that the integral from -2 to 2 of f of x is equal to 10. Minus, you could do work here to do this next part, but I want you all to know that you can calculate the integral of the definite integral of a constant really easily by just doing the constant times the length of the interval. So we should all see that this integral here is going to be 6. But we could also do it as 3x evaluated from 0 to 2, and oh yeah, you're going to get 6. So then we're going to get 5 times 1/2 times 10, bless you, minus 3 times 2 minus 0 which is going to be 5 times 5 minus 6, is going to be 19. Stephen King's favorite number. Maybe not his favorite, but he definitely talks about it a lot. Questions about any? Right. No. I'm gonna do the next one on this page because it's right there. So again, if there are other things you want to see, let me know. Here's Parlax test number 4. Solve the following initial value problem. You're given that dg/dt is equal to cosine of 5t e to the 3 sine of 5t. And we're also given that g of 0 is equal to -1. I'm supposed to solve the initial value problem. When someone says solve the initial value problem, what are they asking you to find? Well, right. So they're asking you to find the function, right? The function, in this case, g of t is what we're looking for. So we're trying to find what g of t is. And yes, you're correct. We do need to find what c is to fully answer the question. But first, before we can find c, what do we have to do? Right. So to find g of t, we're going to find the antiderivative of cosine of 5t times e to the 3 sine of 5t. And hopefully, she has made this integral problem relatively straightforward. I think, again, there's a kind of glaringly obvious choice for what we're supposed to do here. We're going to let u equal 3 sine of 5t in our u substitution. Because the derivative of that is almost exactly showing up. The derivative of 3 sine of 5t is going to be 3 times cosine of 5t times 5. I'm going to write 15 cosine of 5t dt. We practically have that perfectly. We don't have the 15, so I'm going to say 1/15 du equals cosine of 5t times dt. And then instead of rewriting stuff, I'm just going to say, hey, look, that part there with that part there, that's what's going to give me my 1/15 d. So when I rewrite this, I'm going to end up getting the integral of e to the u times 1/15 d. Yes, I would put the 1/15 on this one. You could have made a slightly different choice that would also have been perfectly fine. You could have let u equal just sine of 5t, and then you'd be integrating e to the 3u, which is a straightforward. You don't need to do another u sub for that. You just end up dividing by 3. Here we're going to get 1/15 e to the u plus c. Then we're going to plug back in our u, which is going to be 1/15 e to the 3 sine of 5t plus c. And then we can use our initial condition that g of 0 equals -1 to figure out what c is going to be. So this is what we think g of t is. And then we're going to say, but wait, I need to find c. So g of 0 should equal 1/15 e to the 3 sine of 5 times 0 is 0 plus c, and that should equal -1. Sine of 0 is 0, 3 times 0 is 0, e to the 0 is 1. So we have that 1/15 plus c is equal to -1. So c is equal to -1, which is -15/15 minus another 1/15. So c is -16/15. And if you did this, you might be able to convince me to give you full credit, but you really should then rewrite your answer as g of t equal to 1/15 e to the 3 sine of 5t minus 16/15. That's your actual final answer. Again, the solution to an initial value problem is the function, g of t in this case. Back and forth. All right, let's look at Fanjang problem number 4. Fanjang number 4. We'll look at A first. Reiterate, if there's something you really want to see, just raise your hand, let me know. So here's problem 4 from Fanjang. Consider the region R drawn like this. It's not super important what it looks like exactly. So here's your R, which is just all that jazz done. So consider the region R bounded by the graphs of, he meant to write y equals f of x there, but he wrote y equals parentheses x. But he certainly meant to write y equals f of x, which he notes is greater than 0. And this is f of x here. X equal to a, which is also greater than 0. X equal to b, which is greater than a. And finally, y equal to 0, which is just the x-axis. So the region he's described. I don't think you really need to write all that down, but okay. But you get to assume everything's positive, which is kind of nice. So then he says the following. Part A. Sorry, I wrote A again. Oh well. Suppose that f of x, the function you've written, is equal to 4x squared minus x to the 4th, with a equal to 1 and b equal to 2. Find the volume of the solid find the volume of the solid obtained by revolving around the x-axis. Personally, I don't see why you need any of this build up here, but okay. So to find the volume revolved around the x-axis, we're going to think about drawing a little vertical strip, right? Our function is in terms of x, and notably, it would be very difficult, if not impossible, probably not impossible, to solve for x as a function of y. If it's hard to solve for x as a function of y, it means you shouldn't, probably, which means you should definitely be using a vertical strip. Since our strip is perpendicular to our axis of rotation in this first problem, what method do we have to use? Is it shell or is it disk washer? Disk washer, specifically disk, because our region is flush with our axis of rotation. So we're using the disk method here, and we're getting that the volume of our disk is pi times your radius squared times your thickness dx. And in this case, and sorry, I've inappropriately used capital R there when it was used there already. I actually used a little r. I am thinking of this height of our function as our radius. Let me just write radius there. Let me write radius here. So then the height of our function is just f of x, which in this particular case is 4x squared minus x to the 4th. So we've got pi times 4x squared minus x to the 4th squared. So then the volume total is going to be the integral from, they gave us the bounds, x equals 1 to x equals 2, of pi times 4x squared minus x to the 4th squared dx. And the question does say calculate, not just set up. So we actually have to do the rest, which is kind of terrible. So we have to multiply this out. We got pi times the integral from 1 to 2, 4x squared minus x to the 4th squared is going to be 4x squared squared, which is 16x to the 4th, minus 2 times 4x squared times x to the 4th, which is going to be minus 8 times x to the 6th, plus x to the 4th squared, which is x to the 8th. Kind of gross. Here's the amount of work I would show if I was asked to do this and actually calculate it. I would integrate. I'm going to get pi times the 16x to the 5th over 5 minus 8x to the 7th over 7 plus x to the 9th over 9. Why wouldn't you go from 0 to 1? And then you plug in and you get pi times the whole mess of 16 times 2 to the 5th over 5 minus 8 times, I don't know what I'm sure. 8 times 2 to the 7th over 7 plus 2 to the 9th over 9 minus, and then when you plug in 1, I will point out when you plug in 1 to any power is 1. So I would make the easy adjustment of saying I've got 16 fifths minus 8 sevenths plus 1 ninth. You don't need to write 1 to the 5th or 1 to the 7th or 1 to the 9th. And I would stop right there. There's little to no value of going any further. Certainly your time can be better spent on your exam looking at other questions that are worth more points than simplifying the rest of this. But if you have time at the very end, and if there is an expectation that you simplify, then yes, you can go back there and try to make that look more simple. That looks terrible. I wouldn't. Okay. Part B is do the same thing, but now you're revolving around the y-axis. Part B, we might just, well, so same region from 1 to 2, but now we're going around the y-axis. We still are kind of stuck using a vertical strip because again, our function is 4x squared minus x to the 4th. And now, since our strip is parallel to our axis of rotation, we're forced to use the shell method. So the volume of a shell is going to be 2 pi times your radius times your height times your thickness. In this case, the radius is how far you are from the axis of rotation. Your radius is just x in this case. And that's always true for the shell method. Your radius is just the variable that you're integrating with respect to if you are going around the x-axis or y-axis respectively. So if you're going around the y-axis, your radius is just x. If you're going around the x-axis, your radius is just y. If you're going around some different axes, you have to do the subtraction thing, but we haven't really talked about that yet, so I don't want to get too complicated. So here this is going to be 2 pi times x, and the height is still the function. Or I should say the height is the function, not still, because last time the function was the radius. Like that. This one's probably going to be slightly less variable. So our total volume is going to be the integral still from 1 to 2 of 2 pi times x times 4x squared minus x to the 4th dx. And that's not as awful as the previous one. That's a low bar. 2 pi times the integral from 1 to 2. I'm going to multiply the x through before I anti-differentiate. We got 4x cubed minus x to the 5th. Then we find the antiderivatives. We get x to the 4th minus x to the 6th over 6 from 1 to 2. We get 2 pi times 2 to the 4th minus 2 to the 6th over 6 minus 1 to the 4th minus 1 to the 6th over 6. And yeah, you could probably simplify this without too much trouble. 2 to the 4th is 16. 2 to the 6th is 64. I wouldn't reduce this though, because normally I'd reduce that, except I know I'm going to have to add 1/6 to it, so I might as well not. And then minus 1 plus 1/6. So that ends up being 2 pi times 16 minus 1. Negative 64 plus 1 is negative 63 over 6. That reduces to 2 pi times 15 minus 63 over 6 is 21 over 2. And then we can multiply by 2 pi and get 30 pi minus 21 pi, which is 9 pi. What a nice answer compared to the previous one. But again, if I was taking a test, I would stop here. I've evaluated, I plugged in the limits of integration. Did I simplify it? No. But did I get the correct answer, just not simplified? Yeah, I did. We were like, before you even plug in? Interesting. Okay, well then do what your professor said. So I would say, I would feel like there's not much difference between this and that. But yes, you should definitely, if your professor is saying you can stop early, stop as soon as you're allowed to stop, because how do they do which part?
Like summarize like in
So the idea basically is that if you have some region like this from A to B, it's your f of x, looking at some strip like this, then the volume around the x-axis, we have to use the disk method. And it's going to be, well, the volume of our disk is pi times your radius squared times the thickness. But the radius here is just the function height. So the volume ends up being the integral from A to B of pi times your function squared. Very generally.
and then
For the other method, so we go around the y-axis. Well, then our strip is parallel to our axis of rotation, so we have to use the shell method. So now, in the shell method, this strip becomes the height of your shell, and this distance here becomes your radius of your shell.
Yeah.
So then your volume of your shell is 2 pi times your radius times your height times your thickness. Your radius is just x, your height is your function value, and your thickness is dx in this case. And then the total volume would be the integral from A to B of 2 pi times x times f of x dx. And you could change any of these to be in terms of y, right? If you were doing the same sort of shape but oriented adjacent to the y-axis instead, then your disk method would be the integral of pi times f of y squared dy. And your shell method would be the integral of 2 pi times y times f of y times dy.
okay, so it's like always for if it's like around the x-axis we're using this method, if it's around the y-axis we're always using shadow type. Is that what it is? Or
So any axis you can use either method. The real rule of thumb is that you want to look at your region and decide what kind of strip you want to draw. So for example, and I think I did a similar example to this last time, if your function was say something like, I don't know, actually let's say, I'm across that. Let's say our functions are the square. Yeah, that's not free.
I have another from the textbook.
I have an example. Sorry. So if your function is something like, yeah, I don't have that choice though. If your function is something like 2x minus x squared, let's make that 12x minus x squared, then your region looks like this. And there really isn't a good reason to use a horizontal strip here. In fact, it's very challenging to use horizontal. So if this is my case, I'm using a vertical strip. So then my choices are fully determined for me. If I'm going around the x-axis, it's going to have to be the disk method. If I'm going around the y-axis, it's going to have to be the shell method. Because my strip orientation is parallel to that axis, perpendicular to that axis. But if we had some other function that was not so nice, like, that's a good idea, James. Yeah, I like that. Let's say we're the region bounded by y equal to the natural log of x, y equal to 0, and x equal to e, which looks like this. You could technically use a vertical strip here, but integrating natural log of x is kind of terrible. I would rather not integrate natural log of x. And so if I do things in terms of x, I'm going to end up having to integrate the natural log of x, or maybe even the natural log of x squared, which is kind of awful. So I would actually choose to use a horizontal strip here so that my right-hand function is x equal to e. And my left-hand function, instead of writing y equal to the natural log of x, I'm going to think of that as x equal to e to the y. So now if I go around the x-axis, I'm going to have to use the shell method. because my strip is parallel to that axis. If I go around the y-axis, I'm going to have to use not the disk method, but the washer method, because my strip is perpendicular and it's not flush with the axis of rotation. So here, just to set these up, if I was going to do around the y-axis, my volume would be the integral from y goes as low as 0 to as high as that point there is going to be 1. Because if x is e, the natural log of e is 1. And then it's going to be, this is y-axis, so I'm doing washer. So it's my big radius squared minus my little radius squared. So it's e squared minus e to the y squared. dy, don't forget the pi. And that's really not terrible to integrate at all. If you do that, it's going to be pi times the integral from 0 to 1 of e squared, which is a constant, minus e to the 2y, which just ends up becoming pi times e squared times y minus e to the 2y over 2 from 0 to 1. And that's lovely. On the other hand, if I was going around the x-axis, I'd have to use the shell method. So my volume in this case would be the integral of 2 pi times my radius times my height times my dy. So now here's my radius, which is just y, how far I am from the x-axis. My height, aka the length of my strip, is my right function minus my left function. And then you're going to have a dy. You will have to do integration by parts here because you have a y times e to the y, but sometimes you're stuck doing integration by parts.
How do you choose the radius?
For which part? For the washer method or the shell method?
Both just chose the
Okay, so for the washer method, so what we're imagining if we're rotating around here is that let me just draw this picture again. So I'm just going to draw the region of interest. So here we've got the point 1, 0. We've got the point e, 0. Here's e, 1. Here's the graph x equal to e. Here's y equals natural log of x, or x equal to e to the y. And down here is y equal to 0. And I chose a horizontal strip. Let's draw the picture for going around the y-axis first. We go around the y-axis. Let's see, let me think about how I'm going to draw this. Yeah. I'm imagining taking this strip and revolving it around the y-axis, and I'm getting a washer. And if you look here, this distance here is your larger radius of your larger circle. And this distance here is your smaller radius. And so your larger radius is literally the function that's further from your axis of rotation. So my larger radius here is just e, and my smaller radius here is just e to the y. Versus, if we try to rotate this around the x-axis, and I'll admit this next shape I'm not as good at drawing. If I try to take this strip and rotate it around the x-axis, what you're going to get is a thing that looks like this. You've got your little strip, and then you've got this kind of shell. All right, maybe I didn't say that word. And the volume of that shell is 2 pi times the radius, because that's the circumference of the shell, times the length, which is your height, times your thickness, which is dy. And here the radius is exactly that, which is just how high up the strip is, which in this case is y. The height is just the length of that, which is the right minus the left, and the thickness is dy. That's how we're getting there.
The
Okay.
right is the left minus the right.
Right minus the left. Bigger minus smaller. Bigger x value minus smaller x value.
E minus.
E minus e to the y. Right, the right function is x equal to e. The left function is x equal to e to the y.
Yeah.
Okay. Let's continue on. From Fanjing? Sure. So I feel like I was helping someone with this before, and the original problem I think was missing something important. 3a asks you to find the area under y equal to cosine of x times the square root of 1 plus 3 sine x. And at least when I saw it before, the cosine of x was missing. But if you look, I printed out the one that I just printed this out, and there's definitely supposed to be a cosine of x there, which might have been missing when you first saw it. So it's a much harder problem without the, like, it might be impossible without the cosine there. So at least with that, it's a little bit more reasonable. So the problem says, find the area under the graph of this on the interval from 0 to pi over 2. So we're going to set up the area. The area is going to be equal to the integral from 0 to pi over 2 of cosine of x times the square root of 1 plus 3 sine x. I would say that there are two valid choices for you here. You could either pick just sine x. I would probably prefer to pick more. I'd pick u equal to 1 plus 3 sine x. I think that's the nicer. I think that's the choice that's going to be less work. So I'm going to make the choice letting u equal to 1 plus 3 sine of x. My du is going to be 3 times cosine of x dx. So 1/3 times du is going to equal cosine of x times dx. So I'm going to rewrite my integral. I'm going to reorder my integral as the square root of 1 plus 3 sine x times cosine of x dx. I'm going to start changing things. Always dx first. Cosine of x times dx is equal to 1/3 times du. All this stuff is here equal to u. Now watch. When we change this to being in terms of u, we should also change limits of integration. It would be incorrect to write 0 to pi over 2 here. If you don't want to change them and you want to change back to the end, you can write x equals 0 to x equals pi over 2, but you should actually write x equals, because those are x limits, not u limits. I would change them, and I think you should change them because I think it's easier. So if x equals 0, u is going to be 1 plus 3 times sine of 0, which is 1 plus 0, which is 1. And if x is pi over 2, u is going to be 1 plus 3 times sine of pi over 2. Sine of pi over 2 is 1, so we get 1 plus 3, which is 4. I'm also happy about that because I know that I can take the square root of 4 and get a nice number, and the square root of 1 and get a nice number. So I'm thinking that makes sense. My limits of integration look like they're going to turn out to be relatively nice to plug in here, which is a little more obvious here than it was here, I think. So now we're going to rewrite this so that we can anti-differentiate it. You don't have to, like, I imagine you all be like, oh yeah, that's u to the 1/2. When we anti-differentiate that, we're going to get u to the 3/2 times 2/3 times this other 1/3 that's hanging out, evaluated from 1 to 4. So really I have 2/9 times 4 to the 3/2 minus 1 to the 3/2. And yes, you should simplify this in my opinion because it does simplify. 4 to the 3/2 is 8. It's the square root of 4 cubed. And 1 to any power is 1. So you really got 2 times 7 over 9, which is 14. The second part of this question says, explain why the function is never negative on this interval. Oh, he even does say, give the result as a simple fraction. I feel like that part's kind of weirdly at the end. So why is this function never negative? Well, paper. So why is y equal to cosine of x times the square root of 1 plus 3 sine of x, never negative, or maybe you could say non-negative, on the interval from 0 to pi over 2. Well, 0 to pi over 2 is kind of famously which quadrant of the unit circle? the first quadrant. And in the first quadrant, what do we know about all the trig functions? They're all positive. So we know that, hey, cosine of x is for sure greater than or equal to 0 when x is in that interval. And so is sine of x. So certainly cosine of x times 1 plus or something positive, non-negative, times the square root of something also non-negative is for sure going to be non-negative. I think it's perfectly fine to just say this, though. I think that's a reasonable enough explanation. But I guess you could say these are non-negative, and then cosine x times the square root of 1 plus 3 sine x. Well, certainly that's bigger than or equal to 0. And all this is bigger than or equal to 1, really. So certainly this is bigger than or equal to 0.
What can we find the area by using the definite integral?
I did. It's still using the definite integral, though. I couldn't directly anti-differentiate it. I don't know what the antiderivative of that is off the top of my head without doing the use of. But this is still, we are still calculating the definite integral. We're just using u substitution to get there.
Okay, so u substitution makes our work easier, right?
I would say possible. It makes our work possible. Not just easier, but actually doable. All right. Someone has asked for the question. I was hoping no one would ask for it, but I understand why you would ask. Someone asked for Fanjang number 1. Yeah, I might save that till the end. No, I'll do it right now. Okay. So yeah, Fanjang number 1. It's kind of a gross question. It doesn't feel like a question. No, I'll save it till like the last 10 minutes. I'd like to do other questions that are more applicable to everybody. And then if you are in Parlax class and you want to leave when I do that, that would be fine. Yeah. Sorry, say it one more time.
So it's like another way to do it instead of.
Oh yeah, you could have for this integral, you could have made the choice, which I think is just fine, but it's slightly less good in my opinion. You could have made the choice to let u equal just sine of x. Oh, sure. So if you make the same choice, u equal to 1 plus 3 sine of x, then we get to down here where we've got the integral of the square root of u times 1/3 du. You can just say we're going to leave it as x equals 0, x equals pi over 2. We're going to integrate this. We're going to get 1/3 times 2/3 u to the 3/2 from x equals 0 to x equals pi over 2. And then we plug back in what u is equal to. So we get 2/9 times 1 plus 3 sine of x to the 3/2 from x equals 0 to x equals pi over 2. And then we can plug in those values and get 2/9 times 1 plus 3 sine of pi over 2 to the 3/2 minus 1 plus 3 sine of 0 3/2. To me, this feels like more work, but it's fine to do it. But you're still going to end up having to find what 1 plus 3 sine of pi over 2 is either way, right? You're not avoiding doing that. You're just saving it till later. So then we end up getting 2/9 times 3 times 1 plus 1 is 4, and 3/2 minus 1 plus 0 is 1 to the 3/2, and we get the same answer. So either way, you're getting to the same place. And then let's see, you had a question?
I was wondering if you can go over like an example of finding the area between two.
Sure, yeah. Let's see. So let me just let's say we want to find the area between. Let's see, how terrible should we make it? Let's say we have y equal to the. Yeah, do I have an example here? Nope, I don't. It's fine. I can just make it up. Y equal to the square root of 3x. And sure, y equal to. Getting dicey here. Sure, let's go 2x. We're not going to draw it. So these limits of integration might turn out to be terrible because I just made it up. But when you're finding the area between two curves, the first thing you want to do is set them equal to each other to find the limits of integration. So we're going to set square root of 3x equal to 2x, and I'm going to square both sides. So I'm going to get 3x equal to 4x squared. And you know what I'm not going to do? I'm not going to divide by x. So if I did that, I would lose a solution to this equation, and I need all the solutions. Instead, I'm going to bring everything to the right side. I'm going to get 0 equal to 4x squared minus 3x. I'm going to factor out an x on the right-hand side. I'm left with a 4x minus 3. So I've got either x equal to 0 or x equal to 3/4. Nice. Not really, no. So then our area is going to equal the integral from 0 to 3/4 of the top function minus the bottom function. Now, there's a couple ways to do this. This one's going to be extra kind of awful because our interval here is very short. But one thing you could do is pick a value in your interval, and I might pick something that's easy to take the square root of 3 times. So what's a number that's between 0 and 3/4 that if you multiply it by 3, it's going to turn out to be a really nice number to take the square root of? You can't pick 0. I want 3 times something equal to a nice square number. Excellent choice. So if I pick x equal to 1/3, then the square root of 3x becomes the square root of 3 times 1/3, which is 1, And sorry, that's y equal to that. And y equal to 2x becomes y equal to 2 times 1/3, which is 2/3, which is bigger. 1, without a doubt, which means square root of 3x is your top function. So that's going to be the integral from 0 to 3/4 of the square root of 3x minus 2x. And then we integrate. And I was doing a problem similar to this before, and simplifying the square root of 3x actually did not help us get a nice answer. So I would encourage you to do it like this. I'm going to write this as the integral from 0 to 3/4 of 3x to the 1/2 power minus 2x. When we integrate 3x to the 1/2, I'm going to get 3x to the 3/2 times 2/3. What else should I divide by? If I was integrating, I know I ask this all the time, if I was integrating e to the 4x, what would I end up getting? Right, because we always end up dividing by the coefficient of x when we are trying to do these mini substitutions. So here, I'm going to end up dividing by another 3. Because the derivative of 3x to the 3/2 would be 3/2 times 3x to the 1/2 times the derivative of 3x, which is 3. So I need a 1/3 to account for that. Minus x squared from 0 to 3/4. And then everything is terrible. 3/4. Yeah. So we get 2/9 times 3x to the 3/2 minus x squared from 0 to 3/4. And we plug in, we get awful things. 2/9 times 3 times 3/4 is 9/4 to the 3/2 minus 3/4 squared minus 0 minus 0. And yes, we could simplify this. It's kind of, it's not that bad. 9 to the 3/2 is 3 cubed. 4 to the 3/2 is 2 cubed. And 3/4 squared is 9/16. So you get something terrible. You get 3/4 minus 9/16. That can't be right. It could be right. Oh, that's right, yeah. Which is 12/16 minus 9/16, which is 3/16. Fun. So if you have to find the area between two curves and you don't want to or don't feel able to graph it, this is how we do it. We find the points of intersection. So let's say you weren't able to pick a point, like it just felt too hard. Let's say you did all this work. In fact, I got time. let me throw one more quick example at you all. Let's say we wanted to find quickly the area between, let me make something up. Not, I'm sure. Between y equals x squared and y equals 6x. So I would do the same thing. I would do x squared equal to 6x. I'd bring everything to the left side. I'd factor. And I get x equal to 0 or x equal to 6. So I did the integral from 0 to 6. And let's say I really, really thought, I was confident that x squared was the top function. It's not. But let's say I was confident and I didn't check. And I did all the work. So I integrate, I get x cubed over 3 minus 6x squared over 2, which is 3x squared from 0 to 6. Plug in, I get 6 cubed, which I'm going to write as 6 times 6 times 6 so that I can divide to 3 easily. Minus 3 times 6 squared minus 0 minus 0. And then 6 times 6 times 6 over 3 is really 2 times 6 times 6, which is 2 times 36, which is 72. Minus 3 times 6 squared is 108. And I get negative 36. Here's what you should do. Don't go back and spend time doing it the other way. You only have so much time on your test. It is valid, although I would say frowned. Not frowned upon is probably too strong. Just nobody likes it when you do it this way. But what you can do is you can say, well, if I put the absolute value sign around all this, it's always correct. But you have to do it for every step. So absolute value is there, 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 and then say it's equal to positive 36. This is not cheating. This is totally valid. Just nobody likes it. But it's still correct. So if you did all this work and got the negative answer, instead of going back and rewriting it all so that it was like subtracted the right way, I think you should fix it this way. But really, you should try to figure out which function is bigger first. That's going to be the better thing to do. But if you didn't, that's what I did. Someone asked, oh, so the way someone got 1/3, I believe you're asking about the previous one where we said like we were trying to figure out which function was bigger, the square root of 3x versus 2x, and we were between the 0 and what was it, 3/4, I think. Someone said, oh, well, I want 3 times x to be something easy to take the square root of. So they really said to themselves, I think I'm going to let 3x equal 1 and then figure out that x is going to be 1/3. I think that's how I would have gotten the 1/3 there. And they're like, oh, yeah, if I plug in 1/3, the square root of 1 is 1, and 2 times 1/3 is 2/3. That's how I'm imagining someone did it. If we try to go bigger, right, if we try to set like 3x equal to 4/3, sorry, to 4, you get x equal to 4/3, and that's too big. So we can't even go up to the next square number. You have to pick 1/3. It's really the only nice thing. You can really pick anything, but like if you pick x equal to 1/2, I don't really have a good bead on what the square root of 3/2 is, which is why I'm trying to pick a number that I know how to think about how large it is in comparison to the other thing. I certainly know that 1 is bigger than 2/3. I don't know about the square root of 3/2. That's not true. You could say the square root of 3/2 is bigger than 1 because we plug into 1/2 there, right? That's a number bigger than 1. Its square root is still bigger than 1. So you can pick other values. It's just nice to pick something where the square root comes out. Yeah. All right. I'm going to do this Fanjang problem number 1. So the reason, sorry, someone asked real quickly. The reason I added the absolute value here is because I know that when you find the area between two curves, the answer should come out to be positive. My answer was negative. So instead of going back and doing all the work, right, I could have gone back and said, I really need to do the integral from 0 to 6 of 6x minus x squared. And while it wouldn't take me that long to do it, I have only this much time on the test. I can't waste any of it. So I'm going to go back and maybe, I suppose another option would be to not do anything yet, do all the other test work, and then if you have time at the end to go back and do it the right way, you can do it that way. But I think it's faster and saves you time just to put the absolute values on each of the things. But you have to put absolute values on everything. You can't just do it at the end. At least that's true. Yeah. I'm saying the truth. All right, so this Fanjang problem seems kind of funky, but here's what we're given. So I'm not going to write out the formula yet, but here's what we're asked to do in this problem. We're asked to partition, part A, partition 0 to pi over 2 into n subintervals of equal length and calculate the upper sum u. Oh, sorry, and I missed a few words there. Right. And I apologize. We're supposed to be finding, so we're trying to find the area under y equal to sine of x from x equals 0 to pi over 2. Upper sum. Great. Okay, so the partition is just all your x values. If you really actually trying to write the partition is going to be the set 0, pi over 2 over n, 2 times pi over 2 over n, because we're breaking this pi over 2 up, this 0 to pi over 2 up into n equal subintervals. So our delta x is just pi over 2 minus 0 divided by n, which is pi over 2 over n, or more certain is pi over 2n. And then your partition is just all of your endpoints. So 0, and then pi over 2 over n, 2 times pi over 2 over n, and 3 times that. So we can write our partition as this. All the way to the last one, which is going to be your pi over 2. There's your partition. And then we're trying to calculate the upper sum u. Upper sum is terrible. I would really prefer to say left or right, but I'll point out that on the interval from 0 to pi over 2, sine of x is increasing or decreasing? I think it's increasing, right? Think about the graph of sine of x, it looks like this. Yeah. And if a function is increasing, the upper sum is just the sum using the right endpoints, which I have to imagine is by design. Yes, this question. So we're just going to calculate the sum using right endpoints. So our sum, our upper sum u, is going to be equal to the sum from k equals 1 to n of your function values at the right endpoints. So it's going to be your f of pi over 2n times k right? For the first subinterval, the right endpoint is 1 times pi over 2n. For the second subinterval, the right endpoint is 2 times pi over 2n, and so on, and so on, and so on, times our delta x, which we should certainly write out as the sum from k equals 1 to n of sine of k times pi over 2n times your delta x, which is also pi over 2. And we probably need to simplify this as much as possible. So he gives us this crazy formula. It's kind of a crazy formula, which is that sine of h plus sine of 2h plus sine of 3h all the way to, okay, this is where it's kind of terrible. He says sine of mh. I'm going to change m to n because we have an n. We use, or you can change this n to m, I guess. But we have a sine of nh is what we should write to make our lives less terrible. And that's going to equal, here's the formula, cosine of h over 2 minus cosine of n plus 1 parentheses times, n plus 1 half parentheses times h all over 2 times sine of h over 2. Lovely. I will point out that what I've written right here is really just the sum from k equals 1 to n of sine of k times h. So really, I'm just going to use this formula, but I'm going to replace the h with I over 2n. So here's what we've got. We've got that our sum from k equals 1 to n of sine of k times pi over 2n, which our pi over 2n is acting like our h. And then it's going to be all of that times pi over 2n. I'm not really thinking about that right now. All of this I'm just going to replace with that. So it's going to be cosine of h over 2 minus cosine of n plus 1/2 times my h, which is again pi over 2n, all divided by 2 times sine of pi over 2n over 2. All times pi over 2n. Bonkers. And then, so I would say that's our answer to the first part. Partition that of equal length and calculate the corresponding upper sum. So there's our upper sum. And then part B just says take the limit as n goes to infinity. So part B, find the limit as n goes to infinity of all that, which he points out is also the limit as pi over 2n goes to 0. So if n's going to infinity, pi over 2n is going to 0. So here's how I would look at this. You have the cosine parts and the sine parts. So I'm going to break this up as cosine of pi over 2n divided by 2 is pi over 4n. And this part here, if I distribute the pi over 2n, you have cosine of n times pi over 2n is pi over 2, and 1/2 times pi over 2n is pi over 4n. Times, this is where things get real dicey. I'm going to say, I'm going to write this as on top, pi over 2n over 2, using that 2 as the denominator there, over sine of pi over 2n over 2. There's a reason I've done this. I'll explain it shortly. So, letting n go to infinity, or pi over 2n go to 0, as n goes to infinity, what happens to pi over 4n? Goes to 0. What's cosine of 0? Cool. Okay, how about here? Pi over 4n goes to 0. And what's cosine of pi over 2? Cool. And now over here, you have the reciprocal of sine of a thing over the same thing, and that thing is going to 0. I'll remind you that we learned in 21A that the limit as something goes to 0 of sine of that something over the same something is 1. That limit is the same thing just flipped over, and the reciprocal of 1 is still 1. So your answer is 1. Which it should be, because if you actually did the integral from 0 to pi over 2 of sine of x, you would get negative cosine of x evaluated from 0 to pi over 2, which is negative cosine of pi over 2, minus negative cosine of 0, which is 0 plus 1, which is 1. But it's a real awful problem. I couldn't imagine someone actually putting, I would hope no one would actually put this on the test, but if you're putting on your practice test, I don't know. So let's see. What I would say might be a good practice. So another problem that I think of that kind of has a similar vibe to it, where it's kind of awful in this way, is there's a problem on Grant's website, and we actually did it in class a while ago with the square root, where the partition wasn't like an equal length partition. Let me show it to you all real quick just to remind you, but you can all find it on Grant's webpage. Let me just get a new thing here. One sec. Why is the chat? You're in the way. Okay. Grant. There we go. Let's bring it over here. There's Grant's webpage. Look, there's Grant. And if you go over here to 21B, and then scroll down a bit, it's the one that says, I think it's a creative Riemann sum. And this is the example where you're trying to evaluate the integral from 0 to 1 of the square root of x using a Riemann sum. And the partition is not a partition of equal lengths. The partition is 0, and then 1 over n squared, and then 4 over n squared, and then 9 over n squared. So your partitions do have different lengths. And this is one that you can calculate the limit of if you're careful. I would encourage you to read through that. It's also in the notes from class from near the beginning of the quarter. I could see if you're putting this sign one on your practice exam, maybe asking one like this. There are not a lot of examples of things you can do limit definition wise that aren't like just nice polynomials where you use the usual formulas. But if I was going to ask one like that on a test, I'd give a practice like that. The real answer is I don't know what he's going to do. Right? He could do anything. It's hard to say. But I would certainly be prepared for something terrible like that, because why would you put it on your practice exam if you weren't going to have something like it? I don't know. But again, I don't know how much Fanjing is really thinking about what this test is going to look like, because it's probably been a while since he's taught this class. Yeah.
So question 1 for the second part, like delta x is equal to 0.
Yeah, so I was so right. I wrote that here. I just wrote it as pi over 2n. Right, the pi over 2n is the delta x. But really, you can look at it either way. N going to infinity has to mean that the pi over 2n is going to 0, which is the delta. It's the same thing. Yeah. I think the reason you wrote it that way is because you could think of this as like this, specifically this part right here. You could think of it as delta x over 2 over sine of delta x over 2. So maybe it's a little more obvious that you've got like the sine of theta over theta kind of thing. Maybe that's why he's writing it that way. But I don't actually know. I forgot we go to 4:30, not 4:20, right? We got 13 more minutes. Okay. So now that we've churned through that terribleness, are there other questions people would like me to look at, or should I just pick something? Let me get the chat back up here. There's definitely something in the chat. Okay. For part B, when infinity is substituted for n, where does the second one come from? Right. So I think I just kind of explained that. So I'll say again, right? What we end up having is we have the limit as n goes to infinity of, I'm going to kind of again, it's real gross here, pi over 2n over 2 over sine of the same pi over 2n over 2. If it helps, you might think of this as the limit as n goes to infinity of 1 over sine of, I'm going to write this as pi over 4n just so it's not quite so terrible to write, over pi over 4n. And then we have the limit of sine of some stuff over the same stuff. And where's the stuff going to? If n's going to infinity, where's pi over 4n going to? 0. And when you have sine of something over the same exact something and something's going to 0, that limit is 1. If you really wanted to, you could use L'Hopital's rule, right? Technically right here, you have a 0 over 0 type. If n's going to infinity, top's going to 0, bottom's going to. So if you really wanted to make your life even more complicated, you use L'Hopital's rule and say, okay, well, the derivative, oh my goodness, let's write it as pi over 4n over sine of pi over 4n. And you get the limit as n goes to infinity of pi over 4 times n to the negative 1 is going to be negative pi over 4n squared. I don't really care though, because the derivative sine of some stuff is cosine of the same stuff times the derivative pi over 4n is again negative pi over 4n squared. Those cancel and you get 1 over cosine of 0, which is 1. So you can do it that way too if you wanted to. It's kind of awful. All right, let's be done. Is everyone left in here still in Fanjang's class, or? Okay. Let's see. I feel like, let's see. That's most. Yeah. Let's look over here. Oh, I like this question. I think this is a good question that makes you think. Show that if f is continuous, this is problem 5 from part left. If f is continuous, then, and really you could use any number as your upper limit here. The number that they have chosen is pi. So the integral from 0 to pi of f of pi minus x, show, is equal to the integral from 0 to pi of f of x. But really, you could pick any number. You could pick 0 to 13 of f of 13 minus x equals the integral from 0 to 13 of f of x. This is a great question if you know what to do. So the problem here is we don't actually have a function, right? You can't actually integrate this because I don't know what the antiderivative of my function is because it's just f of x. If you've got a function where the inside of the function is not just x, usually a pretty good bet you're going to do a u sub for that stuff that's inside. So we're going to let u equal pi minus x. We're going to deal with this half. Because that's the one we can manipulate. And then my du is going to be negative dx. So negative du is equal to positive dx. And this is an example of where the reason I like this question is because it's kind of forcing you to have to change limits of integration. You really cannot do this problem without changing limits of integration. So if x equals 0, what's u going to equal? Everybody. Or nobody. If x is 0, thank you. And if x is pi, what's u going to equal? Right. Pi minus pi. So then rewriting the integral, it's going to be the integral from u equals pi to u equals 0 of f of u times negative du. And then, of course, since our limits of integration are out of order and we have a negative sign out in front, it seems like why wouldn't you rewrite it as the positive integral from 0 to pi of f of u du. But then that is literally the same as that. The only difference here is I'm using a u instead of an x. But this integral is actually the same as the integral from 0 to pi of f of whatever variable you like, d that variable. We did it. We showed that that was equal to that. I would ask a question like this. I think it's a good question. It makes you think a little bit. Okay, they're all making you think, but like this one I feel like is a little bit outside of the norm, maybe. Oh yeah, I like that question too. Let's look at the next one. Let's look at problem 6 on our test. So we're given y of x equal to the integral from 1 to 5x squared minus 3 of 2 to the negative t dt. I don't know, you can use the big integral there. And we're asked to find y dy dx. Okay. So this is kind of a one-shot answer. If I'm finding the derivative of this integral, what am I doing with the 5x squared minus 3? Plugging it in for the t. So I'm going to get 2 to the negative 5x squared minus 3. And then what do we need to multiply by? The derivative of 5x squared minus 3. That's our answer. That part right there is just 5x squared minus 3. Nothing else to say then. See here. I feel like there was something else on this again, but looked good to me. The first page. Yeah, this is good. This says I feel so looking at parallax midterm, and someone asked me to, and I'll be happy to. I'll post both classes practice midterms on campus, so you can see the other classes if you want to look at it. The first two pages have a lot of questions here. The first page has 4 indefinite integrals. The second page has another indefinite, and then 3 more definite integrals. Ooh, here's no, I don't think that one. Yeah. So none of them feel particularly like out of line. Trying to see. Okay, here's a good one. Let's look at this one. The integral from 2 to e plus 1 of the natural log of x minus 1 over 5x minus 5. That's a little tricky. That feels pretty tricky to me. So when I'm doing a definite integral and I have to do more than just simplify the integrand, I would much rather do the indefinite integral first and then go back into the definite part. Meaning I'm going to start off by just doing the integral of natural log of x minus 1 over 5x minus 5. I see a mixture. I'm either going to try u sub or integration by parts. What should I try first? I would always say what? U sub every time. Even if it's not going to work, I would still think about it. Can I do a u sub here? So here, there is actually a good u sub. It just is hiding. I'm going to let u equal the natural log of x minus 1, which is also what I would choose if I was doing integration by parts. I would let u equal the natural log of x minus 1, and then dv would be the rest, which is 1 over 5x minus 5 times dx. But here, my du is 1 over x minus 1 dx. I do actually have that. It's just hiding a little bit. I can rewrite my integral as 1/5 the natural log of x minus 1 times 1 over. I factored out the 5 from the bottom, and there's an x minus 1 there. Sneaky. So there's my du. There's my u. So really we have the integral of, I should say, really we have 1/5 the integral of u. Du, which is just going to be u squared over 5 times 2 is 10, which is then going to be the natural log of x minus 1 squared over 10. And the reason I like to do it over there is because then I don't have to carry the e plus 1 and the 2 with me the whole way. So then I can go, okay, great, I'm going to use that, and then say that this is equal to the natural log of x minus 1 squared over 10, evaluated from 2 to e plus 1. Plug in the e plus 1, and you get the natural log of e plus 1 minus 1 squared over 10 minus plug in 2, and you get the natural log of 2 minus 1 squared over 10. That's going to be the natural log of e, 1 squared over 10, minus the natural log of 1, which is 0 squared. We get 1/10. So look out for those u subs, right? When I looked at this first, when I wasn't looking that closely, I really thought it was going to be integration by parts. But it's still good to try a u sub because maybe it's going to work. Just like, yeah, I got a minute here. Just like if someone gives you the integral of, let's see. Sure, minus 6 minutes. Let's see. Sorry, 1 sec. If someone gives you something like this, yes, the bottom factors is x minus 4 times x minus 2. You don't want to jump straight to partial fractions. It's a method of later resort. Because here, before you try partial fractions, you should look at, oh, if I let u equal the bottom, my du is 2x minus 6 dx, and 2 times du is exactly the numerator. So look out for those u substitutions, where another method is plausible, but almost always, without a doubt, u sub is going to be the easiest thing you can do if you have to do something. So I would say, just check. Think about it. If I let u equal that thing, is its derivative there, or is a multiple of its derivative there?